So next up, we have learning how to draw organic compounds. So this is not necessarily explicitly the next section in your textbook. However, I wanted to go ahead and show you and get you guys on on the train pretty much in terms of drawing molecules, how I will be drawing them, because the faster you get into drawing them like this, the faster you will be able to do it well and easily and quickly. Therefore, let's just do it. So when we draw organic compounds, we typically don't draw them the same way that you guys would draw them for your general chemistry or your C101 class that you guys took, or even in your high school chemistry class. You wouldn't have drawn them this way. How you would have drawn them is called the expanded structural formula. So, for example, if I told you to draw propane, this molecule here, C3H8, you would draw 3 carbons in a row, and you would draw all of those hydrogens off of it. Notice how long this is taking me. We'll get to that in a minute. So this is how you would draw it. However, this is not fully accurate. The carbon atoms don't really lie in a straight line. So how you're showing this molecule here is all the carbons just straight across, where in reality, that's not how they look. We know that an atom with 4 things around it will typically show a tetrahedral shape. So I'm going to hide my video in case it's covering it. This picture up here on the top, sorry, I was using the wrong thing to point. This picture up here on the top is what propane actually looks like. You can see that it has a zigzag shape. It's not, the carbons are not in a straight line. And then those hydrogens are pointing out kind of in weird directions. They're not 90-degree angles from each other. They're that 109-degree angle that we learned back in C101. So a better way to draw this would be to draw the 3D expanded structural formula, in which we just draw the same thing. Ooh, that was a bad line. The same thing, but now it's going to be in a zigzag line. And then in order to show wedges and dashes, or things coming out towards you and back into the paper, we draw wedges and dashes. So we'll have a wedge and a dash, a wedge and a dash, wedge and a dash. So this is showing those 3D properties. 3 hydrogens are coming out towards you, 3 are going back into the page. So for example, if I had drawn this carbon, carbon, I'm up here on the picture on the top. This hydrogen is wedged out towards me. You can see that this one in the back is dashed. Same up here, got a wedge and a dash. This one's in line. This one's kind of in line. This angle on this picture is a little bit funky, but this hydrogen is nice and wedged out towards us. This one's going back. So wedges and dashes are how we show 3D. However, what I was saying before, you notice this took a while to draw. I don't really like spending a long time drawing things. When I do my research, I'm typically working with things that have more like 10 to 20 carbons on them. And so if I had to draw out every single carbon and hydrogen in my research molecules, it would take me forever to draw these out. And additionally, you as students don't want to sit there and draw out every single little thing when you're on your exam and you're rushing for time. So I'd rather you guys spend that time thinking, not spending that time trying to draw in every single little thing. So we're going to use what's called a skeletal formula, which is the most common representation of a organic molecule. In skeletal formulas, we'll start with what we assume, and then I'll show you what they look like. Each carbon we assume is tetrahedral. We assume each carbon has 4 bonds, even if they're not shown. And lastly, any bonds that are not shown are bonds to hydrogen. So if we just leave out a bond altogether, there's nothing else there, That means that you fill out the rest of those bonds with hydrogens. So a little caveat here, just so you guys know, if anything is not a carbon or hydrogen, we leave out the C's and the H's, but if anything is not a carbon or a hydrogen, then you have to draw the symbol for that. So we're going to leave out the symbols for carbon and hydrogen, and we're going to just show the bonds in between them. So all I will do for a skeletal formula for propane is this right here. I'm actually going to move it over to explain it a little bit more. So we have, if I just draw this, what this means is that I have a carbon atom at each of the points of the line, and I'm only going to draw the bond in between. Then, because we assume everything not connected, or without anything not shown is a bond to a hydrogen, then I can assume that this carbon has 2 hydrogens in the middle. This carbon here on the end has 3 hydrogens because I need to have 4 bonds per carbon. And then on the other end, I can also assume that I have 3 hydrogens. So as you're learning, oh, I didn't turn my video back on. Whoops. As you're learning, go ahead and draw it just like I did. In the second one, where you can put the carbons on there and draw out all of the hydrogens. After about, I promise you, after about a week, this feels really weird, but after about a week, you're going to start learning and start being able to do it without those hydrogens and without drawing in those carbons, if you commit to it. So as you start like, oh yeah, I got this is fine. Start dropping those hydrogens, dropping those carbons, and just draw it with your stick figures is what a lot of people call it. So let's practice it. Oh, I'm sorry, I skipped over a slide. We are going to talk about why we know that carbon is tetrahedral. So the question is, how did chemists first figure out that carbon is tetrahedral? Well, because it was first proposed to be like how you were drawing it before, which is a square planar molecule. So in 1868, they proposed that carbon was completely flat and had 90-degree angles between all of the hydrogens, and then the tops and bottoms were completely open. But if you look at the molecule dichloromethane, CH2Cl2 is what you call that, or what the chemical formula for that is. You can have 2 just different isomers of this molecule. You can either have the chlorines right next to each other, or you can have the chlorines on the opposite side of each other. If this molecule is completely flat, that would mean that these 2 molecules would have very distinct properties. They are different. One is symmetric. I guess they're technically both symmetric, but they're symmetric in different ways, right? So you would expect different properties. You would expect to see 2 separate properties when you use any kind of analysis method or data collection on it. However, we know that it's tetrahedral because we only see 1 isomer of product, or when we take pictures of it, pretty much is the simplest way to say it. So we know that it's tetrahedral because no matter how you arrange these atoms around this carbon, it's always going to be the same arrangement. You can switch things around, but there's always going to be 2 chlorines kind of near each other and 2 hydrogens kind of near each other. So because we only had 1 set of data from there, we know that it's tetrahedral. So now we're going to do some practice in terms of taking our, how we used to draw chemical or organic molecules and draw them in our skeletal formula. So what I like to do first, especially when I was learning, is to number the carbons. So let's start on this first one. We're going to put number 1 and then a number 2 on the carbons. I'm going to put my pencil down, and that is where carbon 1 is going to start because we only draw the bonds. And then I'm going to draw a zigzag line up and count 2, and that's all I have, 1 and 2. 1, 2 carbons. So just for safety and learning, we're going to go ahead and draw in those carbons. Whoa, how am I doing that? Draw in those carbons, and if you need to, draw in the hydrogens as well. So this is overall what we're showing in this molecule. However, our final answer is literally just one line. The angle of the line doesn't necessarily matter. Okay, let's move to the one below it. So I'm going to number the carbons, 1, 2, 3, 4. This one's weird because it's in a new orientation, but since it's tetrahedral, it doesn't really matter. Everything moves around. So let's draw this guy out. Start with put our pen down on the paper. That's number 1, up to 2, down to 3, up to 4. Let's check our work and number 1, 2, 3, 4. Good. And then let's add in some hydrogens to practice. So remember, when we're adding in our hydrogens, we're trying to make sure we have 4 bonds to each carbon. So I'm going to redraw this in the final answer version. Oh, too many. So this, what I'm highlighting, is going to be our final answer. Let's do yellow. What I'm highlighting is our final answer for these molecules. Pause the video, try the next 2 on your own, and play the video when you're ready. So let's keep going with the top one here. 1, 2, 3, 4, 5, 6 carbons this time. We're going to put our pencil down. That's number 1, up to 2, 3, 4, 5, 6. So this is now going to be our final answer. I'm going to move it over just a little bit. And let's draw in our carbons and hydrogens. Or actually, we skipped a step. We need to number them to make sure that we did this correctly. 1, 2, 3, 4, 5, 6. Awesome. So we have 6 carbons. Go ahead, and if you need to draw in those hydrogens, I'm going to hold off just to save time. And our last one, let's number those carbons. 1, 2, 3, 4. I then start with our pencil on the paper, up to 2, 3, 4. And then let's number it. 1, 2, 3, 4. Great. So something you will notice is that these are the same molecules, these 2 on the bottom. So the rotation around the, so you see they started off looking different, but the single bonds can rotate, so those are actually the same molecule. Okay, so here's your answers for your practice. Please commit to drawing molecules like this. It'll save you so much time, and I will be using it for the rest of the semester. So I will see you guys in the next video.